Hey, it's Mr. K. Let's talk about enthalpy. So we've already talked briefly about exothermic reactions. Here is where we're going to start again. And energy is leaving this reaction, going into the calorimeter. By definition, that is exo, it is exiting. So today we're going to talk about all of these different things that define an exothermic reaction in the eyes of a chemist. First of all, energy is going into the calorimeter. So from the calorimeter's perspective, that is positive. From the reaction's perspective, that is negative. So we've talked a lot about Q. This energy being transferred, that is Q. But from the idea, or from the point of view of the reaction itself, this thing has a different name, which is enthalpy, or change in enthalpy. Enthalpy is the total potential and kinetic energy of a chemical system. In this case, energy is going down, Q is going up. So Q, delta H is the symbol that we have for enthalpy. Well, H is enthalpy, delta H is change in enthalpy. And these two are always going to be equal but opposite. Whereas the calorimeter is gaining energy, it is positive. The enthalpy change is negative because we're losing energy. Alright, now for the purpose of high-level chemistry, like our Chem 30 class, we're just looking at the change in terms of the reaction. We don't need to consider the energy of the thermal energy in the calorimeter, except that it goes up or down, and we can calculate that using Q equals mc T. Instead, we're going to use a lot of graphs to represent what's happening here with these energy bar charts. Now, typically, it's not shown like this. The way it's actually going to be shown is with just two flat sections there, where we see the reactants and the products. And it's the same thing here, just reactants, products. You can even think of it as going from 4 bars to 1 bar. And in this case, you can see the energy is going down. So we call that a negative delta H for these exothermic reactions. Another way to show this is with something called activation energy. Now, the reactants are still going to start high, but we're going to consider that a little bit of energy has to be put into the system in order to start the reaction. So here are my reactants, here are my products, that's meant to be flat. These are all just my EP. These could be my time on my x-axis. So in this case, we can see that from this line, this is still my delta H, and it is still a negative delta H. However, there's this new thing where we recognize that we have to put in activation energy to start a reaction. Okay, so there's a couple more things about this. First of all, just looking at the reaction itself. So the way a reaction could be written, knowing this delta H, experimentally these things are studied, documented, so that we have a table of a bunch of enthalpies, more commonly for formations than just reactions. Anyways, so for this delta H, like I said, delta H is negative. So you can either see it listed off to the side here with a negative, or you can see it in the reaction. Now because energy is leaving the system, we can write it over here as a product. And when it's written as a product, it's telling you energy is leaving the system, it is telling you that this is an exothermic reaction. A couple other ways we can know that it's exothermic: the temperature of the surroundings. So like we say, energy is going into the calorimeter, so then the temperature of the surroundings should be going up. And then finally, you'll see this phrase over and over again: energy is blank the surroundings. Energy is released to the surroundings. So the reaction is releasing energy, the calorimeter is gaining it. And then finally, the potential energy. So this is just comparing the potential energy of the reactants and the products. I like to draw this out whenever I'm dealing with it so I can decide. But you can see the reactants is greater than the potential energy of the products. And it's that change of energy that causes that energy to be released or to be absorbed. Okay, let's take a look at the same thing, but this time let's look at endothermic reactions. Okay, so I've left this one pretty blank and we're just going to go through. So in this case, instead of energy leaving the system, energy is going to be going into the reaction. So now the calorimeter, for the first time, is getting colder. And the endothermic reaction, or the chemical energy, potential energy, is going up. The thermal energy, or the kinetic energy, of the calorimeter is going down. Once again, this is my Q, and it's going to have the opposite sign of that delta H. In the case of this reaction, the reaction now is gaining energy, the calorimeter is losing it. This is our definition of an endothermic reaction. The way we show it on these simplified diagrams now is the reactants start low and finish high. So low to high, low reactants to high products. In this case, I have a positive delta H. Okay, looking at that second graph that we mentioned, this one's including activation energy. Still low for the reactants, going higher to the products. This time you need a ton of energy. Alright, so now looking at this system, there are two things. First of all, in order to activate this thing, you have to climb all the way to the top of the mountain. That is my activation energy now. And my delta H is still positive. All of this can still recognize the reaction is gaining energy, positive delta H, positive delta H. All I'm saying here is that these two things have opposite signs. If Q is negative, then I've got negative, negative, which is a positive delta H. Okay, so to wrap things up, let's talk about photosynthesis. So photosynthesis is the most important endothermic reaction that exists. Here's photosynthesis. I could add delta H as a term at the end, and it would be positive to say that energy is going into the system. When I write this as a reaction, I put energy, or sunlight in this case, as a reactant. Okay, going back to my calorimetry example, if energy is going into the reaction, that means it's leaving the calorimeter or the surroundings, so the temperature of the surroundings are going to go down. Well, I'll share a video of barium hydroxide and sodium thiocyanate where we can actually freeze water of the surroundings. In this case, energy isn't being released, it's being absorbed. Energy is being absorbed from the surroundings. And then finally, how do the potential energy of the reactants compare to the potential energy of the products? Well, you can see the products are high and the reactants are low. So the potential energy of the products is greater than the potential energy of the reactants, or reactants are less than products. Okay, so there is our summary of the two. We've got our endo and we have our exo. We want to take a moment and recognize that everything is opposite, or what's much easier, much safer, is to simply work your way through it. I like to start off with the LOL energy bar charts. I can see which way the energy is flowing. I can decide if this is positive or negative. I can think about it as energy leaving the system. I can think about it as the surroundings taking that energy being released to the surroundings. And then from those graphs, I can decide which one has greater or less than potential energy. Okay, you can do this for endo or exo. Again, it's not about remembering, it's about understanding. Thanks for tuning in.